Kc RT, why I'm writing it here? Delta Ng, it's not here. You have to do it yourself. The question has already given you the relationship and you have to interpret it. You have to do it of your own, that what does this delta N signifies? Delta Ng is number of moles of gaseous products, mind it, gaseous only, minus number of moles of gaseous reactants. No solid, no liquid will be considered in delta Ng. So we have gas here, we have gas here, and this equation also seems to be pretty balanced. One coefficient here, one coefficient here. It is a balanced chemical equation. So my delta Ng value will be, I have 1 mole of ammonia in product here plus 1 mole of product, gaseous product in form of HIA here, and ammonium chloride, a salt, is in solid state. So number of moles of gaseous reactant in this case is 0. So my delta Ng value is 2. And it has asked me to calculate the value of delta N for this reaction. So fourth option is the correct option as far as this problem is concerned. Now let's move on to another problem, the second problem of this session. For the reaction, the standard Gibbs free energy value is positive. Now Gibbs free energy value, Gibbs free energy value comes too often. So I would recommend you to remember a very important result which goes like this. It is delta G naught is equals to minus 2.303 nRT log of value of K. Now K is here, K is our equilibrium constant, and base of this log is 10 because I have used 2.303 over here. If natural log would have been used, this equation would have been ln in terms of ln K, but I'm using this equation here. Now it says that delta G for this reaction is greater than 0. If this value is greater than 0, which means this value is positive, now using this equation I can say that log K will be minus delta G upon 2.303 RT. Now temperature used here in this equation is temperature in Kelvin, which is an absolute temperature, so it won't take any negative value. R is also a constant and takes positive value. So if delta G naught is positive, this term will be positive, but by virtue of this negative sign, log K will be negative. Now it is a simple maths that log 1 we know is 0, and let's say I am taking log 2, it will be positive. So if, let me clarify, if log x, let's say I'm calculating the value of y equals to log x. If x is less than 1, y will be negative. Any value which is less than 1, I'm taking its log, it is going to be negative. If x is 0, then y will be, I'm sorry, not 0. If x is 1, log of 1 is 0. And if x is greater than 1, then y will be positive. So any value which is greater than 1, its log will be positive. Any value which is less than 1, its log will be negative. So what I am getting here, log K is negative, which means that the value of K is less than 1. So fourth option will be the correct option as far as this problem is concerned. All right, now let's move on to another problem. Let's move on to another problem. Problem 3. Which of the following is not a general characteristics of equilibrium involving physical processes? I have to read it out for you and analyze each and every statement individually. It is asking me not a general characteristic. So first statement is equilibrium is possible only in a closed vessel system at a given temperature. Yes, very true. This is one of the important feature of chemical equilibrium, that it should be carried out in a closed vessel, because if, let's say, if gases are involved, if we don't take a closed vessel, then those gases will escape out. So if this is the reaction, this is my reaction, H2 gas plus Cl2 gas gives us HCl gas, and this process involves equilibrium. If I'm not taking a closed vessel, then how I'm expecting that H2 and Cl2 will combine to give us HCl, or HCl will decompose back to give me back to H2 and Cl2. It is not possible unless until we have a closed vessel, right? So this is a correct statement. All measurable properties of the system remains constant. Yes, equilibrium is a state in which factors such as temperature, pressure, volume, quantity of substance, concentration, if there is any color associated with any reactant or product, it becomes constant when equilibrium state is achieved. So this is also a correct statement. All the physical processes stop at equilibrium? No, this is incorrect. Why so? Because not this. Equilibrium is dynamic in nature, which means that at equilibrium only the rate of forward and backward process becomes equal, so that all measurable properties seems to be static. Process doesn't stop. Why so? Let me give you some information, very crucial information. Every process in nature requires a driving force. I'm giving you very important information. Every process in nature requires a driving force. Whether that process is physical or chemical doesn't matter. Two driving forces, or let's say, let me introduce two driving forces I'm talking about. Or let's say two factors. Are responsible. One is delta H and enthalpy change, that is. Another is delta S. Whenever this factor is negative, it drives a process. Whenever this factor is positive, it drives a process. Whenever delta H is positive, it opposes a process, and whenever this factor is negative, it opposes a process. So it's an important information, please mind it. I'm going to use this signs, symbols, how they are driving, how they are opposing in coming problems as well. So delta H, whenever delta H enthalpy change of a process is negative, it drives a process, means it favors a process. Whenever delta S of a process is positive, again it favors a process. So we have to take care of these signs. If delta H is positive, it opposes the process, while if delta S is negative, it opposes a process. Now, as far as equilibrium is concerned, we have two processes. Let's say A is giving us B and B is giving us A, which means that we have two processes simultaneously going on here. One in forward direction, another in backward direction, which means that I'm going to have a driving force for the forward process and a driving force for the backward process. Let's say this happens to be the case for this process. Delta H is negative and delta S is also negative. This means, students, that forward process is favored by delta H. It is driving a process. Now delta S is negative for the forward process, means that it is opposing the forward process, but it also means that it is favoring the backward process. See, this delta sign is negative as far as forward direction is concerned. If for forward direction delta S is negative, then for backward direction, the reverse process, delta S sign is going to be positive, and in that case it is going to favor the backward process. So if a factor is opposing a forward process, then it also means it is favoring the backward process. So as far as this process is concerned, forward is favored by delta H and backward is favored by delta S. So I have a driving force, let's say I'm putting it here, for forward direction, and a driving force, this one is for backward direction. Let me take another example. If for a process C gives us D, delta H is positive, it means that it is opposing my forward process, and delta S is also positive, it means that it is favoring my forward process. Then forward process is driven by delta S, forward process is opposed by delta H, means that backward process is favored by delta H. So this is how I am going to use the information from the second law of thermodynamics, or the thermodynamics per se. Now what I'm doing is at equilibrium, what happens is the driving force, these two driving forces becomes equal, but I will have to do certain adjustment. Students, the unit of delta H is kilojoule per mole, and the unit of delta S is kilojoule per mole per Kelvin. So these two quantities, it has units of kilojoule per mole and it has unit of kilojoule per mole per Kelvin. So these two factors doesn't have the same unit. To make it dimensionally consistent, what I am doing is I am multiplying this factor delta S with T, temperature in Kelvin, so that this Kelvin goes from here and this T delta S has the same unit as that of delta H. Now by multiplying with temperature, and temperature is in Kelvin, the sign of delta S won't be affected because temperature in Kelvin is always positive. It's an absolute temperature. Now what happens at equilibrium? At equilibrium, these two forces, one for the forward process, one for the backward process, will be equal to each other at equilibrium temperature. Now what I am saying, at equilibrium there will be a driving force for the forward direction, there will be a driving force for the backward direction, because two processes are taking place and every process requires a driving force. So I have two driving forces here. But at equilibrium, what will happen? These two driving forces will have same magnitude, and here comes the role of the temperature, which makes the magnitude of delta H to be equal to T delta S. But did I say that these two factors will be zero at equilibrium? No, these two factors has become equal to each other. It doesn't mean that these two factors are cancelling out each other. No, that's not the case. These two factors will still be there. So I have driving force for forward as well as backward. Their magnitude are same, means that rate of forward will be rate of backward. So things will seems to be static, but processes has not stopped because the driving force has not reduced to zero. All the physical processes stop at equilibrium. This is incorrect. I have given a lot of time to this statement only for the reason that I'm going to use these signs of delta H and delta S later in other problems as well. The opposing processes occur at the same rate and there is dynamic but stable condition. Yes, this is the meaning of this statement, that driving forces are there, opposing processes are taking place in forward or backward direction means here, and they are taking place at equal rate, which is stabilizing all the measurable properties values. Now third option was the correct option for this problem. Now let's move on to the fourth problem, which is related to the value of equilibrium constant. Let's do it. PCl5, PCl3 and Cl2 are at equilibrium at 500 Kelvin in a closed container. Closed container is essential for equilibrium to achieve. And their concentrations are given to us. These concentrations are at equilibrium. The value of Kc we have to determine. So the expression for Kc goes like this. Concentration of product raised to the power of their stoichiometric coefficient. This reaction is balanced. It is balanced, multiplied by concentration of Cl2 1 upon concentration of PCl5. Is there anything I'm missing here in writing expression for this Kc? Yes. I should mention that these concentrations are at equilibrium point. They are at equilibrium point because there is another term which is not here in this problem, but let me give you some information, which is reaction quotient Qc, which also has the same expression. But students, keep that in mind. An important thing here, that Qc can be calculated at any temperature, which means that while calculating Qc, I can put concentration of reactant and product at any time during the reaction. But for equilibrium constant, I need to write the value of equilibrium, value of concentration only at the equilibrium point when reaction has been the state is such that rate of forward is equals to rate of backward reaction. So I have been given these two values, so there is no need to bother about Qc here, but it's an important thing here that this expression requires putting concentration value only at the equilibrium point. So I have also been given the value of these two reactants and two products and one reactant. Their values are 1.2 into 10 to the power minus 3, 1.2 into 10 to the power minus 3 upon 0.8 into 10 to the power minus 3. I have to do some maths now. 1.44 10 to the power minus 3 upon 0.8. If I divide 144 by 8, it will be 18. So in this case, it will be 1.8 into 10 to the power minus 3. So which option is the correct option? The third option is the correct option. It is 10 to the power minus 3 here. Fair enough. Okay. Let's do this question now. It is based on statements. Let's do it. Which of the following statement is incorrect? In equilibrium, mixture of ice and water kept in perfectly insulated flask, mass of ice and water doesn't changes with time. Now we have a perfectly insulated flask with us, so there is no exchange of heat energy between system and surrounding. So in this closed vessel we have water in equilibrium with ice, or let me write in a standard way. Ice in equilibrium with water. So this is my case. So as there is no ice requires heat energy, this process will be endothermic plus some heat energy to move into forward direction. But as the flask is insulated, there is no exchange of heat energy in between system and surrounding, which means that the quantity of ice and water at equilibrium will remain constant. So it is a correct statement. What I'm looking here? Oh, incorrect one. Let's go further then. The intensity of red color increases when oxalic acid is added to a solution containing iron 3 nitrate, which is ferric nitrate, and potassium thiocyanate. All right, let me give you some information related to second point. This was first. Second, iron in +3 oxidation state. This is my thiocyanate ion, and it combines to give us an imperfect complex. I don't know whether you are aware about imperfect complex or not. All right then, no issues. Let's say we have a bonding here between these two ions. It is our cation and it is our anion. It is an imperfect complex. Perfect and imperfect complexes is a topic related to class 12th. It is a red color complex, but it is an imperfect complex, which means that they can break to give us back ferrous ion and thiocyanate ion whenever it is possible. I mean to say that bonding between or the force between these two ions is weak and they can separate. So if they can separate, they can give us back ferrous ion and thiocyanate ion. That's how this equilibrium process equilibrium state is achieved. Now what has happened? What we have added? We have added oxalic acid here, H2C2O4. Now students, if you figure out the oxidation state of carbon in oxalic acid, it will come out to be +3. That you can work out by using an equation, a simple mathematical equation. Let me give you another information which is very important as far as inorganic chemistry is concerned. A fact: carbon with oxygen has found to be most stable in +4 oxidation state. Now here carbon is in +3 oxidation state. What is going to happen? Carbon will go into +4 oxidation state. So carbon will get oxidized because there will be an increase in oxidation number. So someone else will have to get reduced. Now who will get reduced? If H2C2O4 is getting converted into CO2, I mean +3 to +4, then someone else will have to, here oxidation is taking place of carbon, then someone will have to get reduced. I mean from here we will be getting electron. +3 to +4 means there will be a loss of electron. Then it will go in, ferric will convert it into Fe2+ ion. Now earlier equilibrium was achieved here. As Fe3+ ion is getting converted into Fe2+ ion, there will be a drop in concentration of the reactant. And according to Lee-Chatelain's principle, which governs the dynamics of equilibrium, where equilibrium is going to shift if there is or are any changes, then if we decrease the concentration of the reactant, then this equilibrium will shift in backward direction, and as a result, because Fe3+ is getting reduced into Fe2+ ion, there will be a drop in where we are getting Fe3+ ion from, this equilibrium reaction. Now this Fe3+ ion, if they will get reduced, there will be a reduction in the concentration of the reactant, and due to reduction in the concentration of the reactant, this equilibrium will shift backwards. Now if this equilibrium shift backwards, the number of this ion, FeSCN2+ ion, will reduce, and the intensity of red color will also reduce. Red color is due to higher concentration, more intense red color will be due to higher concentration of this. But as it shifts forward, the concentration of this ion will decrease. The red color will slowly start fading away. Now on addition of the intensity of red color increases. No, due to addition of oxalic acid. No, it decreases. So this statement is incorrect. This statement should have been decrease if this statement would have to be correct. So this is my correct option. Let me discuss third and fourth option for you as well. We might get some new concepts here, or I may be able to give you a revision. On addition of a catalyst, the equilibrium constant value is not affected. Yes, the value of equilibrium constant, I'm not going to discuss this thoroughly, but the value of equilibrium constant only and only depends upon temperature and stoichiometric coefficients of a reaction. Nothing else. Equilibrium constant for a reaction with negative delta H value decreases as the temperature increases. Equilibrium constant value for a reaction with negative delta H value decreases as the value of temperature increases. All right, now let me give you an equation related to the value of equilibrium constant and temperature. The equation is like this: log of Kc2 by Kc1 is delta H upon 2.303 R T2 minus T1 upon T2 into T1. This equation is called Van 't Hoff equation. Kc2 is the value of equilibrium constant at temperature T2. Kc1 is the value of equilibrium constant at temperature T1. If you don't see this equation in NCERT, there is no need to bother. There is another equation, Arrhenius equation in NCERT, where instead of delta H, we have activation energy EA. Arrhenius equation involves activation energy, Van 't Hoff equation involves enthalpy change. Now, equilibrium constant for a reaction with negative delta H value decreases as the temperature increases. Now, if T2 is greater than T1 and delta H is negative, which means that this term will be positive because T2 is greater than T1, temperature is increasing. This term is negative. This overall term will be negative. It is negative, it is positive, overall will be negative. So if log is negative, log of a value is negative, then that term is less than 1. And if it is less than 1, which means that Kc2 is less than Kc1. So with increase in temperature from T1 to T2, equilibrium constant changes from Kc1 to Kc2. And in what manner? Final value of equilibrium constant is less than the initial value of the equilibrium constant, which means that with increase in temperature, delta H value is if negative for a reaction, equilibrium constant value decreases. Yes, this statement is correct. It was also correct. Yes, it is factually correct. This statement is incorrect, and it is asking me to find out the incorrect statement. So the second option is the correct option as far as this problem is concerned. It really was an informative question, an important question as well. We can expect problems of such type. We can expect such types of problem. Now let's move on to another problem. Yes, I'm following the correct order. When hydrochloric acid is added to cobalt nitrate solution at room temperature, the following reaction takes place and reaction mixture becomes blue. On cooling the mixture, it becomes pink. On the basis of this information, mark the correct answer. There is some formatting issue here. It is on the product side. So let me write it for you. It's a coordination compound. If you don't know, just leave it. This compound is colored pink plus 4Cl minus aqueous gives us CO Cl4 2 minus plus 6H2O. This is my problem, and it says that on cooling the mixture it becomes pink, means with decreasing temperature the equilibrium shifts in backward direction because pink color starts appearing. And in the previous problem I have discussed with you delta S, T delta S and delta H. Let's consider these two factors. I have multiplied by absolute temperature T, which is in Kelvin, and multiplying delta S by T will only make same the units of these two factors or these two terms, but multiplying with T will not affect the sign of delta S. Now if delta S is positive, it will favor the forward process. If delta H value is negative, it will favor the forward process. If its value is negative, it will oppose the forward process. Mind my words, I'm saying forward. And if it is positive, it will oppose the forward process. Now with increase in temperature, the equilibrium has shifted towards backward direction. Why so? Because it says it becomes pink, which means that temperature factor should be along with delta S in such a manner so that if I decrease temperature, the reaction shifts in backward direction. Okay, let's do one thing. Here I have pink color and here I have blue color. Let's say delta H is negative and T delta S is also negative. It is favoring my forward process. It is favoring my backward process because it is opposing my forward process. It is opposing my forward process. So delta H will be here, delta S will be here. If I decrease temperature in this case, now the magnitude of T delta S will decrease. If the magnitude of T delta S will decrease, the backward process will not be favored. Backward process will be less favored. So there is a less probability of getting a pink color. Now let me change it. Pink here and blue here. Let me do it this way. Delta H is, let's say, positive and T delta S is also positive, which means it is favoring forward. It is opposing forward, favoring backward. So let me put it this way. T delta S here, delta H here. If I decrease the magnitude of the temperature, the magnitude of forward process, the magnitude of factor that is favoring the forward process will decrease, which means that equilibrium will shift in backward direction. And of course, from blue we will be getting pink color. So this condition satisfies this problem. So my delta H for this reaction is positive. So delta S for this reaction will be greater than 0. Unfortunately, there is some typing error here. Option 1 should have greater than 0 here, and the option 1 should be the correct option as far as this problem is concerned. I'm doing some correction here. Delta S should be greater than 0 and marking the first option to be the correct option. Now, this question is related to pH and temperature. Now, pH, how do we calculate pH? The pH of neutral water at 25 degrees Celsius is 7, yes. As the temperature increases, ionization of water increases. However, the concentration of H plus ion and OH minus ions are equal. What will be the value of pH of pure water at 60 degrees Celsius? Now the self-ionization or dissociation of water takes place in this manner. Self or auto-ionization of water takes place in this manner. Now we have an equilibrium constant Kw here, which is defined as H plus multiplied by OH minus. Since the concentration of H plus ion and OH minus ion in pure water is equal, we will say Kw is either H plus square or OH minus square. So my H plus value will be square root of Kw. Now the relationship for pH is as follows: minus log of H plus ion. So minus log of square root of Kw, This is my pH. Now at 25 degrees Celsius, value of Kw is 10 raised to the power minus 14. So pH will be minus log of 10 to the power minus 14 square root, or minus log of 10 to the power minus 7 minus of minus 7 log of 10 using the properties of log, and log 10 value is 1. So my pH is 7. Now the problem says with increase in temperature, the concentration of H plus ion, ionization of water increases. If ionization of water increases, both the concentration of H plus ion and OH minus ion will increase. both. So at 60 degrees Celsius, what can I expect? I can expect H plus ion and OH minus ion concentration to be greater than the H plus ion and OH minus ion concentration at 25 degrees Celsius. The Kw value at 25 degrees Celsius happens to be 10 raised to the power minus 14. What can I expect? At 60 degrees Celsius, because of increase in ionization, more dissociation of water into H plus and OH minus ion, they are both are equal and they both are increasing. My Kw value will be greater than 10 raised to the power minus 14. It will be greater than 10 to the power minus 14. So let's say Kw at 60 degrees Celsius is 10 to the power minus 12. Please don't get confused. 10 to the power minus 12 is greater than 10 to the power minus 14. So it is greater than 10 to the power minus 14. Because of the increase in ionization, it has increased. Now my pH will be, using this relationship, will be minus log of square root of 10 to the power minus 12. So in this case, we can easily see it will be 6. So I have assumed this value, 10 to the power minus 12. But in any case, it has reduced from 7. So if it has reduced from 7, then less than 7 is the most appropriate option as far as this problem is concerned. Interesting. Let me give you a simple trick for this. Let me clarify. With increase in temperature, pH value of pure water decreases. Now if I take a pH scale at 25 degrees Celsius, pure water pH is 7. Now if I decrease temperature, pH value will shift here with increase in temperature, and with decrease in temperature, pH value shifts to that side, becomes greater than 7. So I can say fall backwards. Remember these two words. With increase in temperature, pH value fall backwards. It comes to this side with increase in temperature. So it is going to be less than 7. So third option is the best option as far as this problem is concerned. Now ionization constant for various acids have been given to us. I have an equation here. For a monobasic acid, weak electrolyte. Monobasic means it can only give one H plus ion. Weak acid. If I dissolve it in water, I will give H plus ion and A minus ion in water. Now for this, if I work out through the equilibrium constant Ka value at equilibrium, this will be the expression. I am going to take the concentration of pure solvent to be 1. My H plus ion concentration, students, will be square root of Ka into concentration of acid. And if I do some pH calculations, minus log of H plus ion using this equation, and I substitute the value of H plus ion here, minus log of square root of concentration of acid, by doing some maths using properties of log, I can easily see that this will be my expression for pH. If you know it, it's Henderson-Hazelbach equation. If you don't, then this is the relationship for pH of a monobasic weak acid. This is the relationship. It can be easily worked out from here. So now it has given us Ka values. Ka values. Now Ka value, formic acid has the highest Ka value. Formic acid, no, not this value, I'm sorry. Formic acid Ka value for formic acid is Ka value is 1.8 into 10 to the power minus 4. For acetic acid, this value is 1.74 into 10 to the power minus 5. And for hypochlorous acid, it is lowest, 3.0 into 10 to the power minus 8. Now pH we can calculate by this relationship. Now in all the three cases, the concentration of acid has given to be the same, 0.1 mole per dm cube or per liter. Now whoever has highest Ka value, because of this negative sign, will also have highest pH value. I'm sorry, whichever acid has highest Ka value, because of this negative sign, will have the lowest pH value. Concentration of acids in all the three cases is the same. Higher the Ka value, higher will be the acidic character. It has also been mentioned in this problem. K is the measure of acidic strength. You can use this point as well here. Lower will be the pH value, and all this holds true when concentration is same. So our formic acid has the highest Ka value, see over here. So its pH is going to be the lowest. Now its pH is going to be the lowest, and followed by acetic acid and followed by hypochlorous acid. Hypochlorous acid is the weakest acid because its Ka value is lower and concentration for these three acids are same. So its pH is going to be the highest. So hypochlorous acid will have highest pH value and formic acid will have the lowest pH value. The fourth option is the correct option as far as this problem is concerned. Now let's move on to another problem. Ka, Ka1, Ka2 overall equilibrium constants values has been given to us. We have to find out the correct relationship between Ka1, Ka2 and Ka3. Now it's a pretty simple problem, easy one. If I add equation 1 and 2, what I am going to see, if I add them, then I'm going to get my third equation. These two will cancel out and this will be my result. And it is the property of equilibrium constant. If two equilibrium state reactions are added, then the equilibrium constant of the new reaction, equilibrium reaction, is multiplication of the equilibrium constant of those reactions which we have added. So we have added 1 and 2 to get 3. So the equilibrium constant of this reaction, which in this case is Ka3, will be simply the product of equilibrium constant of the reactions we have added to get the desired reaction 3. So I believe that the first option is the correct option as far as this problem is concerned. If we would have subtracted these two equations, in case of subtraction, the resulting equation will have an equilibrium constant which will be the division of the equilibrium constants of two reactions which we have divided to get a desired reaction. Now let's move on to another problem. It is related to acidity, again a very important concept. Now as far as concepts are concerned, there are three concepts for acid base in our chemistry. First is Arrhenius concept, which is related to H plus ion for acid, OH minus ion for base. Bronsted-Lowry concept, which is related to loss and gain of H plus ion. And third is Lewis concept, which is related to lone pair of electron. Acid are acceptor of lone pair of electrons, provided they have vacant orbital or orbitals. It is orbitals here. Mind my writing. Base is lone pair donor as far as Lewis concept is concerned. Now in BF3, this is the electronic configuration of boron. Boron only does bonding in the excited state. Why so? Because in excited state it will be able to participate in more number of bonds and will get more stabilized, because each and every bond formation leads to release of energy. Higher the number of bond formed, more stable will be the molecule. But even you see over here, even after doing bonding in the excited state, boron is unable to complete its octet. It still has a vacant orbital, and which is kind of concern as far as boron is concerned. It has a vacant p orbital. It doesn't have any H plus ion or OH minus ion for that matter to think that it can behave as an Arrhenius acid or base. Acidity of BF3 can be explained on the basis of, see, it has vacant p orbital. We can place some electrons here to fulfill its desire for completion of its octet, or to fulfill its to fully fill its vacant orbital. So it will be an acceptor of lone pair of electron. I'm giving you an example here. Nitrogen has a lone pair which it can easily share with boron. So if this happens, then nitrogen will be able to convert its lone pair into bond pair, and boron will be able to complete its octet and will be part of an additional bond, which will give it more stability, because after 3 bonds it will be forming another bond. So its acidity, it's an acid because it is a lone pair acceptor, can only be explained on the basis of Lewis concept. So third option is the best option. Let me give some more information. As far as Bronsted-Lowry concept is concerned, a base is a substance which is an H plus donor. So ammonia is also an H plus donor. Why so? Because if it does so, then it will be able to convert its lone pair into bond pair. So essentially a Bronsted-Lowry base should have a lone pair over it. So ammonia has a lone pair and it is sharing its lone pair. So ammonia has a lone pair, it can accept H plus ion, it is a Bronsted base. It is also acting as a Lewis base here for the reason that it is capable of sharing its lone pair. So if ammonia would have been asked about its basicity, then fourth concept would have been a better option, because ammonia can accept H plus ion because of its presence of lone pair, which is the definition of a base as far as Bronsted concept is concerned. And Lewis concept says that a base is the lone pair, which ammonia is certainly. So ammonia would have been asked related to its basicity, not acidity, then fourth option would have been the best option. So I have given you some information. Okay, now let's move on. Which of the following will produce a buffer solution? Now a buffer, let me give you some information. I'm not going to discuss buffer thoroughly because it will require at least 1.5 hours. Buffer is of two types. Buffer of a single substance, which is a salt made up from a weak acid and a weak base. Let me give you an example. Ammonium acetate. This salt has been formed by a weak acid, acetic acid, and a weak base, ammonium hydroxide. And we have second type of buffer, buffer of mixture. Buffer of mixture, which is further of two types, acidic buffer and basic buffer. Now, okay, this question involves buffer of mixtures, and for an acidic buffer, what do we desire for an acidic buffer? A weak acid plus its salt with a common ion. Let me give you some information, or sorry, example here. I'm using this space. So we have a weak acid, like we can have acidic acid plus its salt with a common ion. Which ion is the common ion here? I presume acetate ion is our common ion here. And as far as basic buffer is concerned, we again need a mixture. I hope you have written this information. Basic buffer requires a weak base plus its salt with a common ion. For example, and this example pertains to this question of ours, ammonium hydroxide is a weak base plus ammonium chloride, which is a salt which has, both of them have ammonium ion as the common ion. So how I am going to develop this basic buffer as far as this mixture is concerned? Now in first, second and third option, and even in the last option, we have been given a base and an acid. Now let's work out the first option. Ammonium hydroxide will react with HCl. It's a simple neutralization reaction between an acid and a base. So what I'm going to get? Ammonium chloride and water. Now, if I wish to have a mixture of weak acid and salt with the common ion, what I need to do? I need to think whether the number of moles or the quantity of ammonium hydroxide is greater than HCl. If this happens at the end of the reaction, I'm going to have ammonium hydroxide as leftover because it is in excess, and ammonium chloride as the neutralization product of ammonium hydroxide and HCl. So if number of moles of ammonium hydroxide is greater than number of moles of HCl, at the end of the reaction, it will be totally consumed. Some part of ammonium hydroxide will be left over, and a neutralization product of ammonium chloride will be there. And it makes a lot of sense because of the reason that we will have a weak base and its salt with a common ion. So from first, second and third option, we have to find out the number of moles of ammonium hydroxide and HCl. And the examiner has made our life easier volume of these two samples for acid and base are equal. So I only need to see their number of moles. Oh, I'm sorry, moles are already given. No, this is molarity. Again, I'm sorry. This is molarity. So number of moles can be calculated very easily from this relationship, molarity into volume. But I have to only consider the molarity for the fact that equal volumes are given. So I have here 0.1 moles per liter. So number of moles of ammonium hydroxide in first case is 0.1 V, and number of moles of HCl are also 0.1 V. This information, this case will not work out, because at the end of the reaction we will be only having ammonium chloride, no ammonium hydroxide. Now in second case, if you again use this relationship, you will find that ammonium hydroxide number of moles will be 0.05 V, and some maths is involved, you can easily do it, and 0.1 V for HCl. In the end I will have some HCl, but it's a strong acid, not a weak acid. And strong acid are not at all involved in any kind of buffer solution. In third case, I have 0.1 V of ammonium hydroxide and 0.05 V of HCl. It makes a lot of sense, and perhaps this is the correct answer, for the reason that at the end of the reaction, as ammonium hydroxide number of moles are higher than HCl, some ammonium hydroxide will be left over and some salt, weak acid and its salt with a common ion. So this is the correct option. And for the sake of completing this problem, I am discussing the last option. We have a salt here and a base here. So there will not be any reaction between a salt and a base. So I'm not going to get any neutralization product. So there will be no reaction, no buffer formation. It cannot be a buffer of a single substance, because though we have acetate ion is a part of a weak acid, sodium ion is part of a weak base, and buffer of single substance, a salt, which is a salt, requires that cation and anion should be part of weak acid and weak base. So third option is the best option as far as this problem is concerned. So it was a lengthy problem, but buffer solution is an important concept. We frequently get such type of problem in our examination. I have discussed with you in brief the types of buffer and how buffer of mixture can be formed.